Is it visible?
Yes, sir.
Okay. Okay. So, good morning to everyone. We are discussing about current mirror circuit, active current mirror circuits. So, previously, in the last class, we discussed about the same thing, large signal and small signal analysis. Now we are going to large signal analysis. Now we are going to small signal analysis. Yeah, small signal analysis. This is the, what is this one? 5 transistor
OTA.
Yeah, for this we need to do the small signal analysis. Okay. To analyze small signal properties of the circuit.
Sir, getting more disturbance. Ask anyone to mute.
Okay, I will do one thing. I will go to the next tab. Wait. Okay, now it's okay. Hello, is it okay now?
Yes, sir. Yes, sir.
Yeah. Okay. So next one is small signal analysis. This is the 5 transistor OTA. So for doing the small signal analysis, what to do? First, assume the gamma value 0. That means consider no body biasing is required. Okay. So now my question is, for this circuit, okay, this is what? To calculate the differential gain of this circuit, can we apply half circuit concept? Okay, half circuit concept can be applied only when the circuit is symmetric. The circuit is symmetrical. Okay, so as in the figure, with small differential inputs, the voltage swings at node F and X are vastly different. So I want to show once again the picture. 5 transistor OTA. This is, so here this is the node F. This is the node F. Node F, and this is the node X. This is the node X. Okay. So in this circuit, this is the input, and this is one more input. Okay, this is the node F, this is the node X. Due to these two inputs, due to this input, this is the output. Due to this input, this is the output, maybe you can say. See, the swing of this signal at the node F and the swing of the signal at the node X, looked at carefully. So I think both are very different. Am I correct? Swing I am talking about. Okay, swing means height. So both are very different. Okay. So now this is the asymmetric swings in differential pair with active current mirror. Of course, the circuit, you know, differential pair with the active current mirror load. This is the different circuit. So asymmetrical swings. So generally, if the circuit is symmetry, the whatever the swing here must be the same swing you should get. The swing should not be changed. But what happened? So here is the swing is different, and here is the swing is different. This I can call it as a asymmetrical swings. Okay, so that is the you observed in this one. So why these swings are different at node F and X? Okay, since this configuration is M3 configuration is the diode connected device, and M4 is not like that. Since M3 is the diode connected, so the gain at this diode connected output is less compared to this one. So the gain of this fellow is small and the gain of this fellow is very large. I hope you understand. So diode connected configuration will yield less gain compared to the open device. Clear? So lower gain. Lower gain means what? Lower swing you will get. So as a result, the effect of the voltage at node F and the voltage at node X. So this is the P. P is another node. Okay. Because of these two asymmetries, because these two are different, what happened? The effective node voltage at the P will not cancel it because this is this direction. This is this direction. If both are same, both will be cancelled, and the P is acting as a virtual node, virtual ground. Since in this case, so this swing and this swing is not opposite but not equal, so that they won't cancel each other, so that there will be this node P, no way it is acting as a virtual node. Got my point? Hello?
Yes, sir.
Yes. See, this is as a result, the effects of the VF and VX at node P through R01 and R02. Okay, so do not cancel each other, and this node cannot be considered as a virtual ground. What do you mean by virtual ground? So whatever the voltage at this point, the same voltage can be appear here. So even though some devices, some component is available in this between them, that is called the virtual ground concept. Okay, so but now earlier the voltage at the P is 0. So this is the ground. So same voltage will be reflecting. So that I can call this node P as the virtual ground. But now because these two nodes differently amplifies the signals, okay, they won't cancel each other at that node P, so that some voltage will be there. So I cannot say now the node P is the virtual ground. Next. So now I think gain equation is always this one. What is the gain equation? So mod AV is equal to GM is multiplied with the R out. Okay. So R out is the output resistance and GM is the transconductance of the circuit, short circuit transconductance. GM is the short circuited transconductance. Okay. First, perform an approximation analysis so as to develop insight and then carry out exact calculation of the GM. So we have to find the gain of this OTA. Okay. So in the small signal analysis, we have two approaches. One is the approximation analysis. One more is the exact analysis. Approximation. We'll go for the approximation analysis first one. Okay. To calculate the GM, consider the figure. The circuit is quite symmetric, but because the impedance seen at the node F is relatively low and the swing at the node, this node is small. The current returning from the F to P through R01 is negligible, and node P can be approximated by a virtual ground as this one. See, this is the picture. Same picture. Okay, what is this picture? Go to A. Once again, this short circuited. So this current is coming like this. This is the output. Output current is coming like this, and one input is carries the Vn by 1 plus, and one more input is carrying the voltage of minus Vn by 2. Okay. So earlier the problem of this fellow is the node F and node X will not be act similarly. They act differently. So that so the P node P we cannot call it as a virtual ground. Now I'm saying that let a little bit this circuit is let us say or assume symmetry, not quite symmetric. Okay, the circuit is not quite symmetric. Okay, so but because the impedance seen at the node F is relatively low, the impedance seen at this node F is relatively low, small. Okay, so compared to this fellow, and the swing at this node is small. When the impedance is small, of course, the swing of the signal is also low. The current returning from the F to P, this is the current returning from this. This is the direction of current flow. Okay, current returning from the so F to P through R01. This is the R01. Okay, is negligible since the voltage is small. Voltage is low. So the whatever the current is flowing from this side is, let us say, low and negligible. And node P can be approximated by the virtual ground as this one. Yeah. So at this moment of time, okay. So you can split this like this, You can say this is the off circuit concept. Yes. In this case, whatever the node P is, you can say it is a what? Virtual ground. Okay. In the approximation analysis. So take this circuit OTA and current is applied through this to the output terminal. Okay, so so none of the voltage is applied here, but current you can say this is the output current, and you know the difference between the node F and node X. Node F is whatever the signal at the node F is small, and the signal at node X is large, which means the current flowing in this branch you can neglect. So whenever you are neglecting the current flowing in this one, then you can read a circuit like this, and you can say the node P is acting as a virtual ground. So this is the circuit for the calculation of the GM. Okay, and this circuit is the circuit of A with node P is grounded. This is grounded means so this ISS is open, then this node P and ground is directly connected. So in this case, ID1 is equal to, what is ID1? The current flowing in this branch is equal to whatever the other element is there. M3 is there. The current to the M3, that is the ID3. These two are same. And because of current mirroring concept, so this current and this current is same. So that ID1 is equal to ID3 is equal to ID4. This is equal to how much? GM12 is multiplied with the Vn by 2. GM12 is multiplied with the Vn by 2 is the current. Okay. What about the ID2? This is the ID2. Second M2 device current is ID2 is equal to, so minus GM12 Vn by 2, because of the input signal is minus Vn by 2 is multiplied with minus GM, minus Vn by 2 is multiplied with the GM12. This current is, the current in this branch is plus Vn by 2 is multiplied with the GM12, differential gain, okay, differential transconductance gain, as ID2 is equal to minus the input signal is multiplied with the transconductance. So now I out. This is the I out. You know this current. This current is how much? Minus GM12 V in, and this current is so GM12 Vn by 2. If we add these two currents, if you add these two currents, 1 minute, this side current and this side current. So I out is equal to, I can write ID2 plus ID4. What is ID2? Already you know this is the minus, so GM12, so V in by 2 plus this is, what is that one? The V in GM 1 to V in by 2. You can take the mod, then you can take it plus, then this is the, what happened? So GM12 into V in. This is the gain of the circuit. Understand? This is the capital. So you can write this as, I out is equal to this much, total current is minus GM1 to V in. So because V in by 2 plus V in by 2 is the, so V in only, okay. So by virtue of active current mirror operation, this value is twice the transconductance of the circuit figure shown. If you remember this one, what is it? By virtue of the active, I think here we are using the active current mirror load. So the value is twice the transconductance of the circuit shown in the picture. So in the next slide, see, this already we know the circuit. This is the differential pair with the current source load, but it is not active load. Okay, so here already we have calculated the GM values. Here we got the GM 1 by 2 or GM 2 by 2. So the value of this GM is, capital GM is equal to here in this circuit is, so either GM by 2 or so GM 2 by 2. This is. But in this picture, in OTA, see, what we got? GM value is only GM. Capital GM is equal to small gm. So in the earlier picture, so it's a half of the GM. So that the conclusion is, by virtue of the active current mirror operation, this value is twice the transconductance of this circuit. Exactly. Understand? Okay.
Yes, sir.
The GM, capital GM value, capital G suffix small m value in the differential phase with current source load is, what is the value? GM or GM2 by 2. But in OTA, its value is only GM12. Yes. Now, yeah, this already, you know, this we need to find the R out of the same circuit, this circuit only. This circuit R out I want to find. The circuit R out is, we know, calculation of R out is less straightforward. Summarize that the output resistance of the circuit is equal to this one. The output resistance of the circuit is how much? 2 times the R0, 2 is multiplied with the R04. 2 times this is the ground, these two are series, and this is parallel. So that you can say simply the R0 is equal to, so 2 R02 is multiplied with the R04. So now our R0 circuit is, for this circuit OTA, 1 plus GM2 R02 is multiplied the R degeneration plus R02A is approximately 2 R0, this value. So it follows that this is the value. So gain value is this much for about this circuit. So in linearity, in reality, sorry, however, the active mirrors operation yields difference value because when the voltage applied to the output to measure R out, the gate voltage of M4 does not remain constant. So this is the R0 calculation of this circuit. What is the circuit? Differential pair with the current source. But I want, So OTA. OTA means again differential amplifier with the differential pair with the what? Current mirror. Current source, current mirror. Okay. So in reality, however, the active mirror operation yields a different value. Okay, because when a voltage is applied to output, to the output. So to measure the how can you find the R out value? So apply a voltage source here, and find the current I due to that. Then the ratio of these two is nothing but the R out. Okay. So here the gate voltage of M4 does not remains constant. As long as the M4 gate is not constant, the operation of the transistor cannot so define. So rather than draw the entire equivalent circuit, observe that for small signal ISS, it's open. So now I'm going to get the R out of the OTA. So to find the R out, apply Vx voltage and assume the current due to the Vx is Ix. And I already told you, whenever you are going to find the output impedance, all ideal sources should be replaced with the internal impedance. So that here is a, generally here is a ISS is there. ISS is there. It is open circuited. Okay. Understand?
Yes, sir.
Yeah. ISS is opened. And to find the R out value, Vx voltage is applied and find the Ix due to the gate. Yes. So now any current flowing into the M1 must flow out of M2 because both the gates are grounded together. So I can replace this M1 and M2 with a resistor RXY whose value is 2 times the R012. Any objection? Since
No, sir.
both the sources are joined together and gates are joined together, so that I can replace these two devices with a resistor, okay, whose value with the value of 2 times the R012. Okay. Yes. See, here is already replaced. And this M3 is a direct connected, so that I can write this is a what? A resistor of 1 by GM3 is parallel with the R03, and M4 should be as it is. Okay. Yeah. As a result, the current drawn from Vx by RXY is mirrored by M3 onto M4 with unity gain. What it means? The current drawn from Vx. How much current is drawn from the Vx by the resistor? This one. How much current is flowing into this way, this side? Whatever current is flowing this side is mirrored by M3 on the M4. The same current is flowing here. Same current is flowing here, sorry. With the unity gain. The current is equal to, the current going is this one, Vx is the voltage by Vx by the resistance. What is the resistance? It's 2 times R012 plus. So this is the value of this resistor. So that plus 1 by GM3 is parallel with R0. So this is the current. This much amount of the current is flowing through this branch. Understand?
Yes, sir. Yes, sir. Yes, sir.
So now multiply this current by 1 by GM3 parallel with R03 to obtain the gate to source voltage. So what is this voltage? So what is the voltage? Sorry, this is not this. This is the gate to source. It's the gate to drain. What is the voltage between these two? So because the voltage between these two is nothing but drop across this fellow. What is the drop across this fellow? Already you know the current through this branch. This is the current. It should be multiplied with this resistance. So that, so VGS4 is equal to, so Vx by this total is multiplied with the resistance of this M3 is 1 by, so GM3 is parallel with R03. Okay, so now this is the gate to source voltage of M4. So what I told you earlier, the gate voltage of M4 is not constant. The gate voltage of M4 is not constant because here the Vx value, VGS4 depends on the so many parameters. So many parameters. What are there? Vx value, external voltage applied, and so R012, GM3, and R03. So these are the values depends on. So this is the Ix. Ix is nothing but current going this side plus current going this side. This side current already you know. This is the this side current. What is that one? Vx by 2 R012 plus 1 by GM3 is parallel with R03. This is. So, and this side current is, you know, VGS. Okay. From this VGS, you can find this is the this one. So 1 plus 1 by GM3 is parallel with R03 is multiplied with the R04 plus Vx by R04. This current and this current. Okay. So total Ix current is this much. So once you know this current, once again I am going to tell you, this is the circuit for the calculation of the R out. Okay. Here the modifications are, since the ISS is open and these two transistors M1, M2 becomes what? Same gates and sources are joined together. Okay. So it can be replaced with a simple resistor whose value is Rxy, whose value is Rxy is equal to R012. R012. So once it is replaced like that, and this M3 device is diode connected, so that whose resistance is this much. Okay. So now, because of this current, the Ix is coming like this. This is the Ix current. I can say this is the some. You can say this is the I dash. This side current is. Okay. So now this current. This is the I dash, and this is the Ix minus I dash. Ix is equal to. Okay. So this is the Ix current, and VGS is the voltage at this point. Is this current is multiplied with this resistor? That means 1 by, so GM3 is parallel with R03. Okay. So next, you need to find this current. What is this current? Okay. So this is the Vx value. Let us say this value is R04. Then this side current is simply Vx by R04. So then total current is this current, and this current is this much. This plus this is the multiply with the this one because of VGS4. Okay. So that is. For 2 times R012 is far greater than 1 by GM3 is parallel with R03. We have R out is approximately equal to R02 is parallel with R04 only, very small value. So because the approximation is here, what is the approximation? 2 times the R01, twice of the R012 is greater than 1 by GM3 parallel with R03. So this is, here is there and here is there. So this is large, you can neglect this. You can large, so you can neglect here. Okay. So similarly, so here also you can neglect this one. So that finally you got, so R0 means what? In both the cases you have a Vx in the numerator. So R0 is equal to, you can say R out is equal to Vx by x. Vx by x. After taking the common, then if you find the Vx by x, you will get the R naught. With this approximation, your R naught value is approximately R naught 2 is parallel with R naught 4. So now the overall voltage gain is approximately equal to, so AV is equal to formula is what? GM is multiplied with R naught. What is the GM value got? GM12. What is R naught for? R naught for R out is getting. So of course these two multiplication are parallel combination of these two, you can say. This is the, so R out value, GM value and voltage gain value. So this gain, whatever transistor OTA, which is higher, which is higher than the gain which we already calculated for this circuit. This is what differential pair with the current source. So this is what differential pair with the active current source. Okay. So how it is means there is we have a formula of voltage gain. GM 1 by 2 is parallel with this one. This is the G. Okay. Here this is the GM value and this is the R out value. But here we got in the OTA, we got GM values, this value is only GM12 and R out value is this is. So R02 is parallel with R04 only. Okay. So if you compare these two, the gain, voltage gain of the OTA is high than this fellow. That's it. The voltage gain of the OTA is higher than the voltage gain of the, what is this one? Differential pair with the current source.
Current source load.
Current source load. Okay. Understand?
Yes, sir.
Okay. So this is the approximation analysis. Now exact analysis I'm coming. So both approximation analysis and exact analysis both are in the small signal analysis only. In the small signal analysis, what we are going to find? We are going to find the gain. What is the gain formula? So AV is equal, mod AV is equal to capital GM is multiplied with the R out. Okay. So now compute both GM and R out of a OTA. So let us determine the GM without grounding the node P by solving the equivalent circuit shown in picture. So earlier, while you are going to calculate the R out, okay, we make it the ground. Okay, that means open circuit. Which one? ISS. This is the 5 transistor or OTA equivalent circuit. So this is the M1, this is the M2 transistor. This is the M3, this is the M4 transistor. Okay, M5 is there, that is open. Okay, so let us determine the GM without grounding the node P. Solving the equivalent circuit shown in the picture. Here, understand, this is the M1 transistor. M1. This is what? M2 transistor. This is the M3 transistor. This is M4 transistor. Understand? Equivalent circuit.
Yes, sir.
Only this part you can take. This is one part. This is one more part. And this one part, this is another part. Okay. Use the subscript 1 to denote both M1 and M2. So generally, so for doing of these two things, instead of 1 and 2, take 1, it is fine. So GM2, you can write GM1, no problem. Since the current flowing downward through 1 by GM3, okay, GM3 is parallel with R03, denoted by the RD hereafter is, so the current flowing this side is how much? This is the current. So minus V4 by, okay, this is a minus V4, or you can say current is flowing this side is minus V4 by RD. What is RD? Already I told you. So I can write this value is RD. So RD, comma, R01. R01 means this is. This is the current. Now I want to find the voltage. So then voltage is equal to minus V4 by RD minus GM1 into V1. V1 is this much. So into R01. So adding this voltage to VP, is the node P. Okay. So node P is the what? Voltage at this point and voltage at this point. You can add. So what is that one? VP is equal to V in 1 minus V1. V in 1 minus V1. That is the VP.
Okay.
So since it's a parallel, all are parallel. It's a VP is equal to V in 1 minus V1. So or you can say from this side. So VP is equal to V into minus V2. So already I told you. So both can be written as a 1.
And registered.
So now the VP value is minus V4 minus GM1 into V1 into R01 means drop across this fellow, plus drop across this fellow is, you can write as V in 1 minus V1. V in 1 minus V1. Then it is a, what is that one? So is equal to V4. V4. Okay. So according to the exact analysis, first draw the equivalent circuit of the OTA. Okay, the 4 transistors. Then just assume a few things, that is the M1, M2. Both the devices subscripts as 1. Okay, and 1 by GM3 is parallel with R3 combination is just assume it is a RD value. Okay, so then you can go for the calculation of the VP value. The voltage at the node P is V in 1 minus V1. V in 1 minus V1. So you can substitute and another voltage at the V4. V4 voltage is nothing but what? V4 is equal to, so V1. Okay, V4 is equal to V1 plus V in 1 plus the voltage across R01. Means you can write like this. This is the way you can write the what equation. So here, so minus to plus V in 1 plus to minus V1. I think is a plus to minus. Yeah, this is minus, this plus, sorry. So plus the drop across R01. Drop across R01 is, R01 is multiplied with the current. What is the amount of current? Already calculated this here is. This is the current. What is that current? So the current is, yeah, minus V4 by RD minus GM1 into V1. This is. This total is equal to, since this is the node voltage here, this both are same, so that we can write as a V4. So recognize the sum of GM2 V2 and the current flowing through R02 is equal to V4 by RD. Why? What is saying? Just is asking. What is the GM2 V2 minus Vn2 minus V2 by R02 is equal to V4 by RD. This is the GM means 1 by you can say GM is nothing but the current into current by voltage. Okay, so minus Vn2 minus V2. What is the V2? V2 is here. V2 is here. V4 is here. V1 is here. Okay, so the sum of GM2 V2 and the current flowing through R02. Okay, so equal to the current flowing through R02 is equal to, you can say that is the I2 or ID2 is equal to, so V4 by RT. So this is this one, and current flowing to R02 is this much. This is equal to V4 by RD. V4 by RD. So this is the V4 by RD. This is the RD value. This is here is. So now obtaining V1 and V4, V2 from these equations in terms of V4 and noting that V1 minus V2 is equal to V1 minus V in 1 minus V into, and I out is equal to this much. So GM4 into V4 plus V4 by R2. So then it is, therefore I out is equal to minus GM1 into R01 is multiplied with GM4 into RD plus 1 by RD plus 2 R01 is multiplied with the, so difference between these two. So this equation and this equation, yeah, you need to add, then you will get this I out value. Okay, then we want GM, capital GM. Capital GM is what? Capital GM is equal to, okay, so I out by, so this one, so V in 1 minus V in 2. Then this is the remains. This is the remains. This is the GM, capital GM value. This is the exact calculation. Earlier in the approximation calculation, your GM value is, capital GM value is, how much you got? So GM value got, so minus GM12 you got. Of course mod, so GM12 I think you got. Okay, now it's the values extended. So now this is, so now we are going to calculate the R out value. R out value means Ix by Vx. Again substitute the Vx value and find the Rx, what is that one? Current value, Ix. Okay. So now Ix by Vx is equal to R out is equal to. So in the This one. This is the Ix value. This is the Ix value. From that equation, you can write Ix by Vx is equal to 1 plus Gm4 Rd by 2 R01 plus Rd plus 1 by R04. That is equal to, you can write 1 plus Gm1 Rd is multiplied with the R04 plus 2 R01 plus Rd by the multiplication of these two terms is the denominator. So now already you know the Gm value. You know the Gm value and R0 value. You can directly multiply to get the gain value. So what is the Gm value is this much minus Gm1 R01 is multiplied with Gm4 into R0 Rd plus 1 by Rd plus 2 R01. So that is, and what is the R0 value? This is the R0 value 1 plus Gm4, okay, into Rd is multiplied with R04 plus 2 R01 plus Rd by 2 R01 plus Rd into R04. If you multiply both Gm value and R0 value, then your gain is this much. Your gain is this much. Okay, so this is multiplied with this one. This is multiplied with that one. Okay, so then this is the final answer. Okay, so what is the Rd value? Already we know the Rd value is R3, R03 is parallel combination with 1 by Gm3. Okay, so after small approximations in this circuit, in this equation, so finally your gain value is this much. Because this combination is nothing but Gm1 is multiplied with the R01 is parallel with the R04. And this is as it is. Or you can say Gm4 in terms of Gm4. Yeah. So after this, okay, approximation solution we got Gm1 is parallel is multiplied with the R01 is parallel with R04. We got something more. This is the another factor is multiplied for this one. This is the approximate analysis. Through approximate analysis, we got this one. With exact analysis, this is multiplied with this correction factor. There's some correction factor. Okay, that is less than unity. Okay, this is the exact and approximation analysis in the small signal analysis of the OTA. Okay, are you okay? Hello?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay then. Any doubts?